So what we're working on in 5.2 is verifying trig identities, right? Verifying using trig identities. I don't know. I would say using trig identities. Hardest word for me to spell. I don't know why. I always mess it up. Got it right that time, though. What I did yesterday is I pulled up a photo. I saved myself a photo of all of the trig identities so that we would have it at our disposal today. Now I just got to figure out where I saved it to. Trig values, verifying trig identities guidelines. That's the one I wanted. So these are the basic guidelines for verifying using trig identities. And I didn't feel like writing them all out. And since I'm recording this, you guys can always refer back to the recording, but I will post this also in PowerSchool. So if you don't want to write it down, it'll still be available to you. But here's what they want you to do. Work with one side of the equation at a time. These are going to be a trig thing equal to another trig thing. And you have to go, well, how did they get from here to here? That's the solution, right? You're showing me how we got from one to the next. So what you're doing is you're going to work with one side of the equation at a time. And you should always pick the more complicated side first, because it's easier to simplify something complicated than it is to expand on something simple to get there. Look for opportunities to factor, to add fractions together, right? Common denominators. To square a binomial, you'll see a lot of difference of squares. One perfect square minus another perfect square. Or create a monomial denominator. That just means one term. Look for opportunities to use the fundamental identities. You have lists of the fundamental identities. Use them. I will repost them in your PowerSchool as well. Note which functions are in the final expressions you want. Sines, cosines pair up well. So do secants and tangents, cosecants and cotangents. If you have that list of identities in front of you, it makes it a whole lot easier. Like I said with 5.1, you should always just have those identities in front of you when you're working while you're getting used to it. When the preceding guidelines don't help, try converting everything to sines and cosines and working that way. Everything can always go back to sines and cosines. Think about that. Secants, right, are just inverse of cosine. Cosecants are just the inverse of sine. Tangent is sine over cosine. So you can always make those things sine and cosine and try and find a way to bring them together like that. Number 5 is the most important one. Always try something, even making an attempt that leads to a dead end can prove insight. If you get it wrong, you know, okay, well, it's not that one. Let's try another identity that might get us there, right? It's a trial and error thing. It is a puzzle, and sometimes you will get it wrong before you get it right. And I know that that is a struggle for a lot of you. A lot of you have a hard time with getting things wrong, and it frustrates you. But more often than not, you know, it's the step you have to take to getting it right. When I went to college, my math professor, my set theory professor, said that being a math major, the one thing you have to get used to is throwing away a lot of paper. Like, you have to get it wrong before you get it right. That's the learning process of math, especially when you get into higher maths. So all that said, let's get into examples, right? Because that's really the best way to learn these things. So our first example is going to ask us to verify secant squared theta minus 1 over secant squared theta is equal to sine squared theta, right? Now, as our guidelines said, we should always start with the most difficult side first. We are showing how this is equal to this. It's all the stuff that happens in the middle. And you know, as a math teacher, I want the work, right? And this whole problem is just asking for the work. It's giving you the answer, saying, how did we get there? So, our how we get there is we're going to take our secant squared theta minus 1 over secant squared theta, and we're going to show how we get it to sine squared theta. Now, I don't always try and figure out like what it's going to. I always feel like if I just look at it and start breaking it down, it's going to get me there if I can notice the things that are going on with it. I know from the Pythagorean identity that secant squared theta minus 1 equals tangent squared theta. It is one of my Pythagorean identities. So I'm just going to write tangent squared theta over secant squared theta. I'll even tell you over here, I use the Pythagorean identity, right? I also know that secant squared theta is 1 over cosine, right? It's the inverse. So since this is on the bottom, I can say that this is the same as saying, if I break it down like tangent squared theta, right? That's the same as saying secant squared theta is the same as saying 1 over cosine squared theta. And if you remember to get that fraction off the bottom, we would just multiply it. So I would have tangent squared theta times this reciprocal, which is just cosine squared theta, right? And I use that inverse property. I know that secant squared theta is the inverse of cosine squared theta because it is the identity, right? It's that reciprocal identity. So I'm just going to say what? Reciprocal identity. Reciprocal. Do you have to list all the reasons? No, I'm just listing them so that you can see what they are. Identity. See, I always mess that word up. So now we have tangent squared theta and cosine squared times cosine squared theta. And I know that tangent equals sine over cosine, right? So I know now that I have sine squared theta over cosine squared theta, right? That is my quotient identity, remember, but tangent always equals sine over cosine. And this is all times cosine squared theta, right? And I can do that. That is my, what was it? What did I say? Quotient identity. I'm trying to do this without looking at my notes because I want to know that, show you like the kind of the thought process and going in. Technically, this is over 1, right? And these I can cross out because when I multiply them, these would cancel each other out. And I would be left with sine squared theta. And that is exactly what we were trying to do. And all I did here was simplify, right? I could have gone ahead and multiplied them together and then crossed out that cosine squared theta, but I didn't have to, right? So what you're showing me is you're showing me how to get from one spot to another, right? We're giving you the answer. You're telling me how I got there. And that's what this entire section is, right? It's giving you problems like that. So we're going to do a few more just so you have a few more examples of them. But that's ultimately what we're doing. Any questions on this one so far? No? Okay. I know sometimes it's hard to ask the questions until you start practicing on your own to know what the questions are. But if you see anything and I do anything that you're like, oh wait, what did she just do there? Please stop me. All right. Because I know it's so hard when I can't see you guys to know if you're getting it. Let's change colors because really the color is the most important thing. Let's do verify that 2 secant squared alpha, 2 secant squared little fishy equals 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha. So what we have here is an addition of fractions. This is my more complicated side. So I'm going to use this one to prove this one, right? It's an equality. It doesn't matter if I work the left or the right. And if you remember, it always says choose the more complicated one. Well, this is nice and simple, right? 2 secant squared alpha. This is the one that's got work going on. So I'm going to work on that side first, right? I'm going to use my 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha, right? And I'm going to try and work my way over to this. Now, these are fractions that are being added together. What do I need when I have fractions that are being added together? I'm kicking it. Thank you. A common denominator. Here I have 1 minus sine of alpha, and here I have 1 plus sine of alpha. So what's going to need to happen is this side needs a 1 plus sine of alpha, and this side needs a, 1 minus sine of alpha. So I am going to multiply this side times 1 plus sine of alpha over 1 plus sine of alpha, right? I have to do it to the numerator and the denominator. The reason I have to do it to both is because that's identical to multiplying by 1, right? We're not changing the value. We're just changing the look of this fraction. This side has a 1 plus sine of alpha, but it doesn't have a 1 minus sine of alpha. So I'm going to multiply this times 1 minus sine of alpha over 1 minus sine of alpha, right? Now, my notes are getting a little ugly, but you'll see how it all works. 1 times 1 plus sine of alpha is just going to give me 1 plus sine of alpha up there. But down here, if I distribute this out, I look at this and I automatically see a difference of squares, right? So I can look at that and go, this is going to be 1 minus sine squared of alpha. But if you want, you can multiply these out and see, right? If I have 1 plus sine of alpha times 1 minus sine of alpha, when I multiply these out, I get 1 minus sine of alpha plus sine of alpha minus sine squared alpha, and these two cancel, right? Minus sine plus sine, and I wind up with 1 minus sine squared of alpha. I just wanted to make sure you remembered how difference of squares works. And this is going to be plus 1 minus sine of alpha over also 1 minus, can't write anymore, 1 minus sine of alpha squared. Right, so when we look at this, now they have the same denominator, which means that I can add these two numerators together and they'll be over the same denominator. So I can ultimately say now that I have 1 plus sine of alpha plus 1 minus sine of alpha all over 1 minus sine squared alpha, right? And if I look at that, that's 1 plus 1, which is 2. Then I have sine of alpha minus sine of alpha. Well, those just disappear over 1 minus sine squared of alpha, right? The next step is, this looks like it's probably a trig identity, right? I'm guessing Pythagorean, right? Because we have sine squared. We can use alpha plus cosine squared of alpha equals 1. So if I just subtract sine squared of alpha from both sides, right, I'm left with cosine squared of alpha equals 1 minus sine squared of alpha. So I know that this right here just equals cosine squared of alpha. So I have 2 over cosine squared of alpha. And check it out. What I'm trying to do is get to secant squared of alpha, right? 2 secant squared of alpha. Well, cosine squared of alpha is the same as saying 2 over 1 over secant squared of alpha, right? They're just inverse functions. So when I multiply these together, right, I'd be multiplying 2 times the reciprocal, and I would get 2 secant squared alpha. Did you need to see that step? Because I know I went fast with it, and I want to make sure you didn't miss how I got from here to here. Or from here to here. Do you know how I got from there to there? You're allowed to say no. You do understand it? Okay. All right. Well, I'm going to show you, I have two more, but one kind of plays similarly. Nah, I definitely want to show you both of them. I know it's time consuming, but I'd rather you guys have the video to see the different types of problems and be stuck in here with me a little bit longer. You know what? I'm just going to show you the converting, and I will do videos of the other two problems on my own and just post them. That way, if you need some more to look at, you have them available on PowerSchool, but you don't have to sit through another, like 20 minutes. So I'll just do the converting sines and cosines problems, and then I'll do the other breaking down example that I had for you on a separate, just little problem video. I might actually go through and solve a few of the odd numbered problems from the section in your homework as well, so that you have video examples of similar problems to the ones you're doing in homework. Because I'm feeling a little bored today, so I thought maybe I'll just do math problems. Not really. I have plenty to do, but I do like doing math problems. So I'm going to skip over to converting sines and cosines. If you remember on that little guide I showed you, it said when in doubt, convert things to sines and so cosines to solve. We're going to do that. We're going to verify two fairly simple problems doing that. So A will be tangent x times cosecant x equals secant x. And B will be tangent x plus cotangent x. Tangent x plus cotangent x equals secant x times cosecant of x. So if we look at part A, we've got tangent of x times cosecant of x, right? And we need it to be secant of x. Well, when I look at this, automatically I know that tangent of x is sine of x over cosine of x. And cosecant is 1 over sine of x, right? Those are my identities, right? This is my inverse of cosecant is 1 over sine. So if I bring these together, I would have sine of x over cosine of x, but I don't have to do that, right? I could cancel these before I even multiply them. And I wind up with 1 over cosine of x. And if I look at that, I know that is just the inverse of cosine, which is just secant. Oops, no, I did not write that. Secant of x. So it's a simple fix when I just converted everything from cosine to from other things to sine and cosine, right? If we look at part B, we've got tangent x plus cotangent x, right? And we need to get to these. And if I look at those two, I know that tangent is sine x over cosine of x plus cotangent, which is cosine of x over sine of x. So we need that famous common denominator, right? We can't add them together. This isn't a multiplication problem. We can't cross anything out. We need a common denominator. This one has cosine of x. This one has sine of x. So this is going to need to have a cosine on the bottom, cosine of x, right? So I have to multiply both sides times cosine of x. And this side is going to need a sine of x, right? So I'm going to multiply those two, right? And when you look at that, you're going to get, this is going to give me sine squared of x over sine of x cosine of x plus cosine squared of x over sine of x cosine x, right? So we have our common denominator, which means I can just go ahead and add those numerators together, which is sine squared x plus cosine squared x, which should look familiar to some of you by now, over sine of x cosine of x. Is it looking a little bit familiar? So our top just equals 1, right? 1 over sine of x cosine of x is the same as saying 1 over sine of x times 1 over cosine of x. 1 over sine of x is just cosecant of x. 1 over cosine of x is just secant of x. And I believe that was what we were trying to get to, was it not? Yeah, cosine, say, secant of x, cosecant of x. I put them in the opposite order, but they're multiplication, so they can go in either order, right? I could have that, I could list that as secant of x times cosecant of x. So those are how changing everything to sine or cosine when you have the opportunity can work for you. There are going to be other problems. I will do them in a separate video that'll just be sample problems. I'm just going to go through a bunch of the homework problems and solve them out, but not the homework problems like the odd versions of the homework problems, just so you can have multiple examples of these things being broken down to refer to. Does anyone have any questions regarding this, or do you need to practice it a little bit to get those questions?